بسم الله الرحمن الرحيم. اليوم بنكمل معكم في لكتشر رقم 12 لكتشر نمبر 12. اليوم بدنا نتكلم عن الفريكونسي دومين اناليسيز اوف LTI systems. احنا تكلمنا عن ال LTI systems in time domain. قلنا انه في التايم دومين the output of an LTI system is the convolution between the input and the impulse response. Today, based on the theorems that we have taken before in the last lecture about the Fourier transform DTFT theorems, وجدنا إنه the convolution in time domain is converted into multiplication in frequency domain. لذلك رح نستفيد من هذه الخاصية ونحاول إنه نشوف كيف نتعامل مع frequency domain analysis for LTI systems. Okay, so today lecture is frequency domain analysis of LTI systems, linear time invariant systems. Okay. As we know, that the output y of n of an LTI system is the convolution of both the input x of n and the impulse response h of n. In other words, y of n is equal to x of n convolved with h of n, and this is the convolution sum. Okay. Now, using the theorems that we have in last lecture, we can say that in frequency domain, y of e j omega equals to x of e j omega times h of e j omega. So it's multiplication. Okay. Now, if we have a single, just a notice here, if we have omega equals some omega 0, then we can say that y of e j omega 0 should equal to x of e j omega 0 times h of e j omega 0. So it's the multiplication of the magnitude and phase of y is equal to the magnitude and phase of x at this particular frequency times the magnitude and phase of h at this particular frequency. Okay. Let's have an example and see what will happen. Example. Determine the output sequence of the system with the impulse response h of n equals to 1/2 the power n mu of n when the input is the complex exponential sequence x of n equals to a e to the j pi n over 2. This is for n in minus infinity and infinity, and a is a real constant. A is a real constant. Okay, to do this, we're gonna do this we're not gonna do this in convolution, we will do this in frequency domain. So we'll go to the frequency domain and do this here. Notice here that x of n has one single frequency, which is omega equals pi over 2 radians per sample, okay? So to do the solution, we will do this through the frequency domain analysis of LTI system, okay? And h of ej omega is equal to, for this system, it is known that this is alpha to the n, and alpha is 1/2, so this one is 1 over 1 minus 1/2 e to the minus j omega, okay? So this is our impulse response. So actually there is a special name for the transformation of the impulse response in the frequency domain. This h is called the transfer function. The transfer function. And the transfer function, because you are transforming the input to the output through this function here, okay? And we will see this later, that from here you can say that h of e j omega is equal to y of e j omega divided by x of e j omega. So it is division in frequency domain. It's convolution in time domain. So you cannot divide y of n over y of n over x of n to find h of n. You have to do the convolution. But here you can divide them in frequency because they are already multiplication. So this one actually is also equals to y of e j omega over x of e j omega. This is why they call it the transfer function. It's the transfer. To transfer the input through this transfer function, you get the output. Okay, so we found h of e j omega. Okay, now our single frequency here for x of n equals a e to the j pi over 2n. We know that our omega here is equals to pi over 2 radians per sample. So it's pi over 2. So our omega 0 is pi over 2. So how we are going to find the output? What we will do is we will apply this equation here. We will apply h at this particular frequency. We have x at this particular frequency, and we will combine those together. Okay? So h of e j pi over 2 is equal to 1 over 1 minus 1/2 e to the j pi over 2. So we replaced omega with pi over 2. So this is equals to 1 over 1 plus j 1/2 e to the minus j pi over 2. This is the phase of minus pi over 2. If you go to this one is here minus j. So it's minus j times minus 1/2, so it's plus 1/2 j. So this one here is minus pi over 2, and this one is minus j. Okay, so this is minus j plus the real part of this one is 0. Okay, so this is actually equals in magnitude 2 over square root of 5 with an angle of e to the minus j 26.6 degrees, or as you learned in circuits, this is 2 over square root of 5 with an angle of minus 26.6 degrees. Okay? Okay, how we are going to do this? We'll do this exactly the same as we did in circuits when we use AC signals. So y of n will be in the time domain is equal to a. Now the magnitude of the new y is the magnitude of x times the magnitude of h at that particular frequency, which is times 2 over square root of 5, and e to the j pi over 2 n times e to the minus j 26.6 degrees. So we multiply this in frequency and we join those together. So this is 2a over square root of 5 e to the j pi over 2n minus 26.6 degrees. And this is our answer. So this is your y of n. Magnitude changed by the amplitude of h, and phase because of the h caused by the phase caused by the h, the transfer function. Okay? Okay. Generally speaking, we'll put this in a general form. So, in general case, if the input to the system consists of an arbitrary linear combination of sinusoids of the form if we have x of n is a linear combination of sinusoids, summation from I equals 1 up to capital L, AI, this is the amplitude of the sinusoids, cosine omega sub I n plus phi I, and this is for n between minus infinity and infinity, then we can say that y of n, taking what we have done here in the example, we can say that y of n is equal to also summation from I equals 1 to n, the same combination, AI, the same AI, but multiplied by h of e j omega I at that particular frequency magnitude, cosine omega I n plus phi I plus theta of e j omega I. Okay? So you have a magnitude changed as here 2 over square root of 5, and you have also phase added positively or negatively as we have here in the minus 26.6. So linear combination of inputs, you have also exactly the linear combination of the outputs with the same input modified by the magnitude of the transfer function and modified by the phase of the transfer function. Let's put this in an example and see how we are going to deal with it. Okay? For LTI system for n LTI system with the following difference equation. Y of n equals to x of n minus, I think it should be, okay, plus 1/2 y of n minus 1. Okay, y of n is equal to x of n plus y of n minus 1. With the following difference equation, determine y of n for the input signal x of n equals to 10 minus 5 sine pi over 2n plus 20 cosine pi n for n between minus infinity and infinity. Okay? We can apply this in time domain and try to see what will happen, but this is not an easy job to do. The best thing to do is to go to frequency domain in such cases, and if we find y of e j omega equals x of e j omega plus 1/2 e to the minus j omega, y of e j omega. Take this one to the other side, so you have y of e j omega times 1 minus 1/2 e to the minus j omega equals x of e j omega. So h of e j omega equals y of e j omega over x of e j omega, and this is equals to 1 over 1 minus 1/2 e to the minus j omega. Okay, which is the same, the impulse response for this one. Actually, h of n is equal to 1/2 to the power n mu of n. Knowing this from the table, you can say that this one and this one are Fourier transform pair. So we find the frequency or the transfer function, the impulse response in the frequency domain, and we will start taking this input here. This input here has 3 parts. You have a value of 10. So this is, we will call this one x1 of n. So x1 of n is equal 10. And for this here, omega equals 0. So our omega 1 is equal to 0, and h of ej0 is equal to 1 over 1 minus 1/2, and this is equals 1 over 1/2, and this is equals to 2 with an angle 0. So actually, the impulse response here said, or the transfer function at this particular frequency says that you will have, if you apply x1 of n with a magnitude of DC value of 10, it will be amplified by 2 with no phase added to this value. So probably y1 that will, that you will get from x1 is 2 times 10, which is equals to 20. Okay, so this is the first part. Now, the second part is x2 of n, which is equals to minus 5 sine pi over 2n, and at this case, omega 2 is equals to pi over 2, and the transfer function of this pi over 2 frequency is equal to 1 over 1 minus 1/2 e to the minus j pi over 2. This equals to 1 over 1 plus 1/2 j, and this is equals to 2 over square root of 5 with an angle minus j 26.6 degrees. Okay, or you can put it in the polar, the phasor form, minus 26.6 degrees. Both are the same. This is the polar form, and this is the phasor form. Okay, and the same thing, the minus 5 will be multiplied by this magnitude, and the phase of the sign will, minus 26.6 will be added to the phase inside. So you have a phase shift here. Okay, the last one, x3 of n, which is equal to 20 cosine pi n, and here omega 3 is equal to pi. Okay, omega 3 is equal to pi, and here h of ej pi equals to 1 over 1 minus 1/2 e to the minus j pi, and this is equals to 1 over 1 plus 1/2. So 1 over 3 over 2, this equals 2 over 3 with an angle 0. With an angle 0. So if we combine all those together, magnitudes and phases to each component of the input, we can figure out what will be the output of the system. So the output of the system, hence the response of the system to x of n is, so y of n will be equals to 10 times the gain, so it's 20 with no phase. The second one, you have 2 over square root of 5 as a gain, multiplied by minus 5, so it's minus 10 over square root of 5 sine the same frequency times n, but you have a phase shift of minus 26.6 degrees, and the third part is plus, the third part is 20 multiplied by 2/3, so it's 40 over 3, which is an attenuation, and the phase is 0, so it's cosine pi n. Okay, no phase added here, no phase added here. You have minus 26.6 degrees phase, and this is the response of your system based on the frequency domain. So this is also for n between minus infinity and infinity. So this is our response for the system with x of n that we have with if we have the difference equation that we give you before. Okay, so this is a good way to analyze time domain or discrete time domain signals in the frequency domain. Okay, with this we come to the end of our lecture. I would like to thank you for being with me, and I hope that you will find this lecture interesting. Thank you very much.